Okay, so now that we've seen the universal quantifiers, let's try to take some phrases, some sentences that talk about all of something or other and write them as formulas. Here is a very simple example. You have a bunch of shapes. Some of them are squares, some of them are circles, some of them are blue, and some of them are white. And here is 4 sentences about those shapes. And some of those sentences are true about the shapes that you see on the screen, and some of them aren't. And in order to see the difference, and in order to figure out which ones are true and which ones are not, we will try to write them. So how would we write something like all squares are white? The way we are going to write them is going to be like this. For every shape, if that shape is a square, then the shape is white. Similarly, we will use the same structure for the other 3 sentences. Every shape, if it's white, it's a square. Every circle, if it is blue, every shape, if it is a circle, then it is blue. And differently, for every shape, if it is blue, then it's circle. So let's try it. How do we say all squares are white? We say for every shape, if that shape is a square, then it is white. Do you think it's true or not? And do you think it's the same as saying all white objects, all white shapes are squares? Well, there, as you see, we will put the implication in the opposite direction. We still say for every shapes, because all of those sentences are talking about the shapes you see on the screen, but rather than saying if it's a square, then it's white, we'll say if it's white, then it's square. Well, suddenly we got something completely different. We have 2 things here that are white, and you know what? Both of them are squares. And yet we got 4 squares here, and only 2 of them are white, the rest are blue. So you see those things are quite different. So let's try a few examples. We had all squares are white, and all white shapes are squares. Now let's do all circles are blue. For every shape, if it's a circle, then it's blue. That's true. All blue shapes are circles. Well, that's not quite true, because some of the blue shapes are squares. And here are some examples from famous logician and also famous children book writer that you might know, Lewis Carroll. All lemurs live on the trees. Okay, we could write it as for every animal, if that animal is a lemur, then it lives in the trees. Is it true or not? Well, I don't know enough about lemurs to really say for sure, but I'd be tempted to say that it's probably mostly true. How about all animals living in the trees are lemurs? Well, now we are talking about something completely different. For every animal, if it lives in a tree, then it must be a lemur. But wait a moment, monkeys live in trees, birds live in trees, insects live in trees. That really doesn't make quite sense. So we say that the structure of those sentences is for every something, if it has first property, then it has a second property. But you may say, wait a moment, why don't we just say for every x in squares, x is white? Isn't it what the sentence is saying? It wouldn't be wrong from the point of view of getting a predicate logic formula, but as you'll see later, this is not very convenient to think about. It's easier to talk about here is a fruit and here is another fruit, and one is more sour than the other. But if you just have apples as a set and oranges as a set, it's harder to compare. So similarly here, you don't want to define predicate white separately as a predicate about squares, and separately as a predicate about circles, and separately as a predicate about triangles and something else. In most cases, it's good to take the set to be as general as makes sense in context. For example, if you're talking about numbers, like integers, you really don't want to go outside of numbers if you want to sum them up or do things with them. But also you don't want to limit yourself to just 1 or 2 numbers. So usually if you have something of the form for every something it is something, we will use the implication and we will make a set to be fairly general. So going back to Lewis Carroll, the famous British mathematician and logician, his name will come up more in the course. He had a wonderful paragraph in his Alice in Wonderland that illustrates that the direction of the implication in those sentences really, really matters. This, as you might have seen, is the part of Alice in Wonderland when Alice is having tea with the Mad Hatter, the March Hare, and the Dormouse. And the dialogue goes like this. You should say what you mean. I do, Alice said. At least I mean what I say. They're the same thing. And then the rest tries to be logical and tell her, no, that's not the same thing. I see what I eat is not the same as I eat what I see. How would we write it as a formula? Well, we say for everything, if I see it, then I eat it. It's not the same as for everything. If I eat it, then I see it, right?